Hi, welcome to Math317 Operations Research. So today we're going to be doing the traveling salesman problem. I'm curious, how many of you have seen the traveling salesman problem? Excellent. How many of you have seen how to solve it using integer programming? Okay, so this is not necessarily the best way to solve the problem, but it is one way to solve it. Before we go forward, I want to just mention an article in the record on the new JA draw system. So this is one of many mathematical proposals I have been making at Williams for years about how to use mathematics to better allocate resources. So the JAs will now get 2 picks their senior year as compensation for being a JA as their junior. The real proposal that I wanted, which has been shot down, was that every student should be given 100 housing points to allocate between their sophomore, junior, and senior years. And depending on how many points you spend, that places you in different spots in the housing lottery. Some people say that this might give a competitive advantage to Math.CS majors. Yes?
So are you also in favor of abolishing the entry system as a restriction on the free market of housing and living?
I will wait until there's a malfunction recording before I answer, am I in favor of abolishing the housing system? I will say I am in favor of mathematizing as much as we can. And I would love to have students get 100 housing points to allocate. Now the real question, going to your free market, is let's say you have 100 points. Do you have to spend them on yourself? Or can you transfer points to friends? And could you have a housing market? And overall, would students be in favor of that? I will leave these as exercises for the administration.
That's why the administration doesn't have that.
Well, no, and that is a real fear, that there are certain people who would then pay a tremendous amount, but other people would probably be very happy to sell their picks for a tremendous amount. All right, so most people have seen the traveling salesman problem. So there's a lot of variants, they're all pretty similar. Essentially, you have a bunch of cities, or points, and you have different paths, and it may not be the case that everything is connected to everything else. And the question is, what is the most efficient way to get from one city to another, to another, to another, such that you hit every city? And there's a couple of different ways you can phrase it. Maybe there's a fixed city, which is the starting city, and there's a fixed city, which is the final city. Maybe you have to return to the start. If you have to return to the start, it's nice, because then you essentially have one cycle. And if you have a cycle, then it really doesn't matter which is your start city. Okay? We will assume a couple of things. What do you want to assume? Well done. What do you want to assume about the cost between traveling between 2 cities?
Triangle inequality?
Okay, so one thing is the triangle inequality. Maybe the cost going from here to here and here to here should be less than the cost of going there directly. Do you think that's a reasonable assumption to make in 21st century America? Why not?
Because we're like transferring flights.
Yeah, sometimes actually with airlines, it is cheaper to fly.
It may also take less time because you spend so much time in airports.
It might actually take less time as well. So depending on how things are, it's sometimes actually cheaper to fly further and fly from this city to that city through the city than to just stop here. So of course, what did a lot of people do in the past? If they wanted to go from here to here, and it's cheaper to fly from here to here through here. Yeah, they just don't take the second flight. Now, the airlines have gotten wise to this, and they will often, if you have a round trip, not let you fly back if you don't complete all segments. We will make certain assumptions just to make the problem simpler. Let's say we're trying to minimize distance traveled. So we will assume that triangle property holds. We'll assume that the distance from A to B is the same as the distance from B to A, or the cost from A to B is the same as the cost from B to A. There's no asymmetry in direction. For simplicity, we might want to assume that every city is connected to every other city. That we have a complete graph. So, I don't want to draw a complete graph with this many vertices, but so here would be an example of a complete graph. So you can get from any city to any city immediately. Any football fans here? So I was recently visiting a colleague of mine, also named Steve Miller, born same year, same city as myself, same thesis advisor, also Jewish. We are fortunately good friends. You almost have to be in a situation like this. And he actually has a really nice article on NFL scheduling. And so the NFL has a wonderful formula for their scheduling. So you play all the teams but yourself in your division twice. Well, that makes sense, you can't really play yourself. You are matched up with another division in your conference for 4 more games. You're matched with another division in the other conference for 4 games. And so this year the AFC East is playing all the teams in the NFC East. So if the Patriots are playing the Eagles, then the Jets will play the Eagles. And then you have 2 more games. And so if you finished 3rd in your division last year, then you play the other 2 teams who finished 3rd in the other 2 divisions in your conference. So there are 4 conferences. What my colleague did is he actually looked at the connectedness of NFL schedules, and he noticed that 2015 is much more split than a lot of other years, and that there's actually a 12-year cycle in NFL schedules, and 2 out of the 12 years, they don't have the same level of interconnectedness. The other one is 2019, and it does allow, in certain years, if you happen to have 2 weak divisions, certain teams can have a little bit of a competitive advantage. And it's interesting that this year we have somewhat of an alignment right now for some teams with some weak divisions. So you do not always have situations where you can get from anything to anything. How many people follow college football? Okay, who's the #1 team right now in America? No, it's Ohio State. They're not ranked #1, but Ohio State is #1. And this is completely independent of the fact that I was a postdoc there for a year. In an ideal world, you would have a lot of games between different conferences, between different contenders. You have very few games. And so you can view a graph almost as these 2 people play each other. The more games you have, the more complete knowledge you have of the system, and the better job you can do ranking. There's a lot of great work, and if people are interested in something like this, this is another more theoretical project. How do you deal with the fact that you have incomplete information, and how do you evaluate, who's doing well in the Big Ten versus who's doing well in the SEC when most schools are terrified to schedule a tough non-conference game, because if you lose, then that's essentially your season. And so most teams try to just win their conference, win the conference championship, and punch their ticket to the national championship in that way. So there's tremendous numbers of situations when you do not have all the information you wish you do. We will assume for now that we always have a path from any city to any city to make the traveling salesman problem a little bit easier. You can easily throw in restrictions that you can't get from any place to any place. And we'll try to minimize transportation times. We'll just care about the distance between cities. One of the restrictions is that you cannot go through any city more than once. That may not be a good restriction to have. Right? And again, you could almost imagine certain types of graph networks, maybe where you have something like this. I think if I have something like this, it's going to be very hard not to go through certain cities more than once. Right? If every city is connected to every other city, we don't have to worry about this. But you might actually want to allow yourself to pass through a city multiple times. One application of traveling salesman is actually making motherboards and computer boards in terms of how things are being drawn and what's the most efficient path to take as you're burning things down. There's a lot of wonderful applications to stuff like this. So what I want to do is I want to talk about how can we attack the traveling salesman problem as an integer programming problem. So we have to be very careful as to exactly what we're assuming. So we will assume a complete graph. So we can start, go from any city to any city. We will have a starting city and an ending city. And then, if we want, why not require that we then have to go back from the ending city to the starting city? So we have to return to where we start. Start and end cities, then return to start. And if we return to start, it actually introduces a really nice feature. So imagine, something like this is the path you take. Because we return to where we started, it really doesn't matter what we consider our starting city. Also, every city on the path now has an interesting property. What is that property?
Degree 2.
Yeah, degree 2. For every city, you leave it once and you enter it once. If we had a start and an end and we didn't have to return to where we started, then we would have two cities that would be a little bit different. But by requiring the fact that we return to where we start, every city, so enter and leave each city exactly once. And that's going to be very nice in terms of setting up our constraints. In principle, if the number of cities is small, is it hard to find the optimal route? What would you do? Try them all. All right. If we choose the starting city and we have n cities, how many possibilities are there?
The next city.
I'm sorry?
What do you mean once you pick one?
Right, so how many paths can we have? Assume the starting city can be chosen anywhere.
N times n minus 1 over 2, choose n.
In fact,
No.
It's
The number of paths, choose n path. No.
We're assuming it's a complete graph, so you can go from any city to any city. How many choices do we have for the first city? And how many choices do we have for the next city? All the way down to times 2 times 1. That's how many possible orderings we have of the n cities. And so we can just check and see which one is best. Now the problem is, this is n factorial, and this is approximately n to the n, e to the minus n, square root of 2 pi n. This is growing terribly fast. This is basically n over e to the n. So it's basically, the square root of 2 pi n is not too bad, but this is basically e to the n log n over e square root of 2 pi n. To give you a sense of how badly it's growing. So this is growing faster than exponential. So when you have on the order of 10,000 cities, this is truly a hog. Okay? So we need a better way to do it. Have we talked at all about how to estimate how fast and how it grows?
Instructions.
Yeah, have we talked about this formula here in this class?
Yeah.
Okay, good. So we know that this is terrible. We know we need something better. I am not saying linear programming is the best way to solve this problem. But for many things, we don't care if we absolutely solve the problem. It's often enough just to be close. Imagine the total route is going to be 180,000 miles. And you can find something that's within 1,000 miles of optimal. That's not horrible. Or maybe even better, something that's within 50 miles of optimal. Right now, we're just trying to find a path. Can you think of any constraints you might want to have, or any things you might want to try to maximize or minimize, other than just the length?
I mean, if we know the price of certain flights and the amount of money spent.
Okay, so one thing is not just distance, but maybe cost. And cost could be a function of time of day, or time of week, or time of month. That it might be cheaper to fly from certain places to certain places, depending on when you are flying.
If we're including time, we might want to minimize the length of the journey in terms of time. Because if we're having to wait longer for flights, that's costing us.
So you could try to minimize how long you're waiting in terms of not doing anything. You might want to hit certain cities at certain times. So a great problem is scheduling games. The Ohio State-Wisconsin game was changed as to what time it was going to be. It was originally going to be a night game, which would not have interfered with the bar mitzvah I was at. Then they moved it up to 12:30. And so one of the family members on my wife's side actually went to Ohio State, big fan. He could have been at the game. And he decided it was better for him to not go to the game and come to the bar mitzvah. But there may have been a small group of us who were occasionally checking scores during the very loud bar mitzvah party. Why do you think the Ohio State game was moved? Money. Yeah, as a rule of thumb, almost anything. When the Red Sox play the Yankees in most years, when do you think those games are? What days of the week? Weekends. You know, Friday, Saturday, Sunday. You're not going to normally schedule the Red Sox Yankees for like the Tuesday, Wednesday games. You want certain matchups to be at, you know, good viewing hours. So a lot of times you can have a feasible schedule, but you can try to put in additional things. You can do this either through multi-objective linear programming, or you can put in additional constraints that you want to try to force. At least so many of the weekend games will involve Red Sox, Yankees, or I think there are other rivalries in sports. You know, Dodgers and, would you do Dodgers, Giants? I mean, again, I'm a little bit biased in baseball, but other sports, you know, NFC East is a wonderful division where everybody hates everybody. And, you know, just sheer hatred. And those are just great games. But you want to be able to put in additional stuff like this. All right, let's start figuring out how to code this as a binary integer programming problem. We need to figure out what our variables are going to be. So what should be the variables?
Indicator variables.
So we need an indicator variable. So what is the indicator variable going to be for?
Are we taking this path?
So that would mean you would have to enumerate all n factorial paths, and you would have n factorial variables. And then it would just be which of the paths is the shortest.
So we would probably need an xijt, basically, where I is the city.
And I'm going to do it in the other order because that's the order we did last time.
Okay. I is the city we're leaving, J is
Right.
the destination, and T is the time.
Good. So it's 1 if at time t leave city I for j and 0 otherwise.
And we can do a simpler version of the problem where T rather than a time is just an order, like
Right.
a term. or
Right.
something.
So in fact, t will go 0, 1, 2, and maybe n plus 1. So at time 0, we leave city 1 for city 2. So maybe we'll start off with city 0, yes?
What do we define J as?
Oh, so for city j. I was just trying to save some time, which now is costing me time. Leaving city I for city j.
Do we have a specific definition? Didn't Jack say it was a city where we're going to end at?
No. He's just saying, at a moment in time, we leave from city I to city j. If that happens, it's a 1. If not, it's a 0. This is very similar to the airlines. Do we have a flight going from city I to city j at time t? Or for the movies, are we showing at a given time on a different screen a given movie? And so the cities will be in 0, 1, 2. And the annoying thing here is always, how do you want to label things? Do you want to have time starting at 0 or 1? Do you want to have the city starting at 0, 1? It doesn't really matter. We just have to be careful. So if I start at time 0 at city 0 and I leave for city 1, then at time 1, I've arrived at city 1. I now leave, and at time 2, I arrive at city 2. So at time n, I arrive at city n, and then I have to go back home. So that would be time n plus 1. So in a situation like this, you know, I would have n plus 1 moves, or I guess n plus 2 moves here. And I'm starting at time 0 at city 0, and then I'm ending at time n plus 1 back at city 0. Yes?
There's not an x for n plus 1, is there? Because xn is going from wherever I is back to j, which is city 0. So it just-
Right, so we don't have a city n plus 1. And so we know we start at city 0. So how do we encode we start at city 0?
Sum x 0, 0, j. Overall j is greater than 0, greater than 1.
So which is it?
Equals 1.
Equals 1. So this would mean that at time 0, we leave city 0 for some city. We could actually change j a little bit more. Instead of summing over all j,
All j not including I.
all j,
Not including 0.
not including 0. You know, we don't allow ourselves to go back immediately to where we started. So this would be, we start at I equals 0. How would it be we end at j equals 0? So what would that be?
N plus 1 and 0
Okay, so it would be a sum of x, you said,
at time n plus 1.
time n plus 1.
The nth city going back to 0.
Right, because we're ending at city n. Although, do we know that we're ending at city n?
We're ending at city 0 by assumption.
Right, but I'm saying, have we specified, we haven't really specified a city that we have to be reaching before we get back to our start.
We should sum over n plus 1 I to 0.
Right, it should be something over I here. What you're saying is you have to go to city n and then go from city n back to the start. We're saying we can have any city as our final city in the final destination. We haven't specified that there's a natural end city from which we go straight home. So this would be a sum over all I, and what I should be exclude? 0. It should exclude 0. So that will force us to return home. Okay, what other constraints do we want?
Only visit each city once.
We will visit each city once, okay. So what would it mean to visit a city? What must happen?
You enter each city. Exactly.
So you enter each city once. So how do you write you enter each city once?
Summing over like all times and all.
Okay, so sum of all times.
And all j.
So this should be a for all I, maybe for every city. Then, if we're entering the city, is that going to be the first component or the second component? Second. So actually, I'll do for all j. It doesn't really matter, but let's use always j's for the second city and i's for the first city. So we'll sum over all times, we'll sum over all cities, and what should that equal?
1.
That should equal 1. So that means you give me any city j, and once and only once do I come into it. Yes?
Should we go less than or equal to go to that city?
But we have to go to the city. This is the traveling salesman problem. We have to visit each and every city. All right, so that would be visit each city once. Now we would need leave each city once. So this would be a for all I, sum over t, sum over j, x t I j equals 1. Does this work? Are there any other constraints we need? Yes?
Only one trip per turn.
Okay.
Per t.
Okay.
So that means for all t, the sum over I and j has to equal 1.
So this is for all I. Oh no, is it? No, it's for all t.
All t.
For all t. The sum over I, the sum over j of x I j. I'm sorry, x t I j equals 1. So this means every moment in time you leave once and only once.
We also need to restrict that I can equal j in the visiting and leaving cases.
Oh, yeah.
Okay, do we need to have that?
Well, right now,
We still don't know that this is a connected path.
Okay, good. So the big issue that we're missing is that it may not be a connected path. Imagine I have something like this. So times 0, times 1, times 2, and then maybe times 3, times 4, times 5. I don't know, can I do something like that? That might satisfy all these constraints. Or another issue I could have is the following. So I'm here at time 0, at time 1 I'm here, at time 2 I'm here, at time 3 I'm here, at time 4 I'm here. So that would work. So what constraint are we missing?
Make sure you leave from the city you came from.
Yes, you have to leave from the city that you arrived at. And if we put that in, I think that will fix everything. So, must leave from city arrived at. Now we've already encoded to some extent that already in the beginning, where we talk about, we want to make sure we start at I and we're leaving I equals 0, we're leaving city 0, and then we want to make sure we return at the end. And then for all the other times, we have to make sure if we've just arrived at city 5, then at the next moment in time, we leave from city 5. Okay, how should we phrase this? Yes?
I would do, for each t,
Okay. What's the range of t?
the whole range 0 to n+1.
Well, we've already handled 0 and n+1. So I think we can do it from 1 to n.
Then I would do, for each city C, this might be the most efficient. I would do then for each city,
Okay.
the sum, for each C, the sum x sub t.
So let's do city I.
I didn't want to do I.
Okay, you don't want to do I? I'm sorry.
Just because I would put it in both places. I would say that sum x t I c
Okay.
equals sum t plus 1 c j.
Okay, so what this is saying is, now do we know that this sum is,
That's summing over all I instead of
and this is
summing
summing of
j.
all I, and this is summing of all j. And C is fixed. So if this sum is 0, then that sum has to be 0. If this sum is 1, that sum has to be 1. And we can't have this have any other value, because we know we only have one trip per turn. So if we sum over I and j for fixed time, we get 1. So since this is a smaller sum, we're not allowing C to vary. We know this sum is either 0 or 1, and this is either 0 or 1. So if this sum is 1, then that means at time t, we've left city I to t. So if 1, at time t, we went from city I to city C. And so now, if this is 1, when then at time t plus 1, we have to leave city C for some new city. So that looks like that's a fine way to code it.
Couldn't we remove the start and end conditions if we just did this mod n or something?
So you almost surely could adjust these things and phrase them a little bit differently.
We just include those in the general, but
Right, and so over here, just knowing that we're somehow starting at 0. I'm sure there's ways to do this. I think it's a little bit easier to just pull those out separately, but you could definitely try to find other ways to phrase this. You could also try to do this with an if statement. If this sum is equal to 1, then, but I think this is a concise enough formulation that works. And we know one of these, as we vary C, has to be 1, because we had this condition over here, which said that we leave each city once, we visit each city once, and we have exactly 1 trip per term. So for a fixed value of t, as we sum over I and j, that sum is 1. So one of these things is 1. So I think this works. Is there anything else we need in terms of constraints? Out of curiosity, how many of you ever played the game Free Flow or Bridges? Okay, so it's you've got different kinds of grid boards, and you have colors, and you have to connect the colors. And if there's bridges, you can sometimes pass, something through a bridge in multiple directions. And every square on the board has to be colored. You have to connect every pair to itself. And you could handle this again very similar to this as an integer programming problem. The question is, you just want to make sure, for instance, that you have a connected path. And that's one of the big questions. How do I make sure that I have a connected path? Well, for every square, when you enter it, do you leave it? And do you leave it with the same color? Can you play games like this? So over here, we have to make sure we're going through in order, that we're not hopping around, that we don't have 2 connected components. And putting in a constraint like this does it. All right, so what's the only thing that we now have to do? Yes? Yeah, we need an objective function. So how do we get an objective function? What are we going to try to do?
Doesn't it depend on preferences?
Oh, no, what? So what's a good set of preferences? Yes?
What would be kind of nice about it, just associate one cost with every x tij?
Yeah, so maybe dij equals dji is cost from I to j. And we'll assume the cost is independent of time. And then we want to just minimize cost. And cost might be distance. So we would want to minimize the sum. So we'd have d ij, and I think just x t I j, with sum over t, sum over I, sum over j. And that's the traveling salesman problem. And for those of you who have seen this before, especially in the computer science class, what can you tell me about the traveling salesman problem? It's bad. Okay? In fact, it's equivalent to, I think, all the bad problems that we care about. So if you could do the traveling salesman problem, then you could do a whole slew of things. And all of these problems we are equally stuck on. But what's nice about the linear programming approach is we are not trying necessarily to solve the traveling salesman problem. By using the dual program, we can often tell how close are we to the optimal solution. And this is wonderful, where you can say, we're within 1/10 of 100th of a percent. That's not bad. And for a lot of things, that's good enough. So it's terrible if you have an algorithm that just keeps running and running and running and doesn't give you anything. As you run this, you will start going through various feasible schedules. Is it hard to make a schedule feasible? No, assuming it's a complete graph. If the graph were not complete, then it would be much harder. And in fact, you might not even have a feasible solution. But because we do, we can actually run this and see how close are we. We may be that far, we might actually be much closer. So just because we're within a certain tolerance doesn't mean we haven't necessarily done much better. But we know we can't have done worse. And that's one of the things I really like about this approach to the problem. These are not hard conditions to write down. And for small values, you can actually run these calculations without too much trouble. Years ago, yes?
Does linear programming change our runtime at all?
In what sense? I mean, there's different approaches to solving the traveling salesman problem. And the different approaches, in terms of comparing what their runtime is, I'm not sure what that is. But again, one of the things that's nice about linear programming is we don't have to run until we get a solution. We can abort the calculation before we get the solution and just say, I'm willing to let the computer run for 2 hours and I'll take the best thing I can get. Whereas in a lot of other programs, it's an all or nothing. You know, if you're trying to determine if a number is prime or not, and you abort the calculation, well, you don't know if it's prime or not. We're lucky here that when we abort the calculation, we actually have some information about how good we are.
Well, I was just curious, since with the thing dynamic programming,
Right.
They actually do something strictly less than factorial. So I was just wondering if there's any direct benefit for us from linear programming with respect to runtime.
I unfortunately do not know what the best runtime is for linear programming and what the different approaches give relative to each other. But here, the point I really want to emphasize is we don't have to solve the problem. And it's unusual to have that in a math class. You know, the goal is to get close. So close only counts in...
Horseshoes and hand grenades.
Okay, I've heard thermonuclear warfare, but hand grenades also works. Right? Sometimes you just have to be close. Now, you should make sure to have all of your parameter values correct. So years ago, we were driving as a family, and the radio was talking about interesting lawsuits. And somebody called up, and they wanted to sue their local paper because they were a fan of baseball, and their goal was to visit every stadium in a year. And they arrived in San Francisco, and the Giants were playing away. And the newspaper said it was a home game. And in an act of true... I'm going to be careful because this is being recorded. Showing their true stripes, the radio host was talking about what a wonderful court case they have and how happy he would be to volunteer his legal services to help this person sue their local newspaper for a misprint in the schedule. For those of you who are thinking of trying to visit all Major League Baseball stadiums in a year, what might you do before you actually go to one of those stadiums? Interesting. You might actually check to see. Yes. So it's an interesting question as to how liable are you for information you put out. Okay, so the last thing I want to do is I want to talk about another application of integer linear programming. Yes?
When you said we don't have to actually solve it, are we running the algorithm a few times?
Well, what often happens is you run the algorithm for how much time you have. And for a lot of these problems, because they take so long to solve, we're not going to get to the optimal solution. But frequently, within 2 hours or 2 days, you get very close to an optimal. If you're going to be making a huge number of motherboards, it's worth letting the program run for a couple of days to get the best solution you can. For other things, if you're only doing it once, it doesn't necessarily matter how much you're off by, as long as you're reasonably close. So there's a whole different level that you can do. All right. So I want to end the day with one other game which you may have seen before. How many of you played Battleship? All right. I think every hand went up on this one. All right. So Battleship, we have 2 players, some kind of wall between them. And you put your ships down in some configuration, and you keep shooting. And you say, I3, and you say hit or miss, hopefully truthfully. Right? And you're not supposed to be moving your ships around, right? So we'll assume honest people playing. And the goal is to sink the other person's fleet before they sink yours. Okay? And there's modifications you can do to make the game more interesting, but we'll just stand with the straightforward game. Okay? Anybody know how to play the one-person version of Battleship? It can't be exactly the same as this because it's not going to be a real mystery. Gee, I wonder where player 2 hit its carrier. Amazingly, all my shots are hitting. Right? There is a one-person version of Battleship. But you need somebody else to set up the game board. So 1, 2, 3, 4. 1, 2, 3. We'll play a very, this is a really simplified version. Let's make it a little bit better. All right. So here is a simplified board. I will imagine I have one of my ships here, one of my ships here, another one of my ships here. 1, 2, 3, 4, 5, and 1, 2, 3, 4. Right? So imagine I put my fleet like this. I'm going to give you numbers. 1, 2, 3, 3, 3, 4.
The second row should be 3.
I'm sorry, did I make a mistake? This should be 3, thank you. Now you can solve it.
Yeah.
2, 2, 3, 3, 0, 5.
I know these are 4 and 4.
Did I make a mistake again?
Not 3 and 3.
Oh, the 4 and 4, thank you. Yeah. You're really not letting me. All right, so if you use the correct numbers, what are these numbers?
The row and column sum.
I'm sorry?
The row and column sum of occupied spaces.
Yeah, the row and column sum of occupied spaces. So the question is, if I give you the row and the column sum of occupied spaces, can you figure out what the fleet positioning is?
Not necessarily.
Not necessarily. Why might we have trouble?
Because, for instance, in those 3 ships at the bottom, you could take the battleship, put it upwards, take the submarine on the right, put it to the left. There are 2 different orientations with this exact same number scheme.
Okay, so if I,
So you take the battleship,
yes,
take it from its right square, and turn it upwards.
this?
So it's in the row with the 4,
Oh, okay, okay.
the second row with the 4.
Mm-hmm.
And then you take the 3 ship and you put it down where the battleship was.
Okay.
So you can basically exchange the positions of the 2 ships, and the numbers don't change.
Oh, okay, yes, okay, I see what you're saying. So what I would do is I have, this is the battleship now, and this is the cruiser. Yes, or the submarine. And so there would be 2 configurations that are the same. So you could do, here's another one, depending on what ship sizes if you have, you could have this, and that would be the same as this, for example. Yes?
But, I mean, in terms of winning the game, those 2 are practically no different.
So then it becomes a question of, what are you trying to do? Is your goal to figure out how the other person positioned their fleet, or is your goal to destroy their fleet? So if your goal is to destroy the fleet, it doesn't matter which way it's oriented. If your objective is, you win if you destroy everything, then the 2 games will be equivalent. If the goal is to deduce the internal structure, this is wrong. Okay. You should be able to set this up as a linear programming problem. What would you try to minimize?
The turns you have to take.
Well, we're no longer really taking turns. You're told the row and the column sums. What are we trying to minimize?
If it's unique, if you don't care about finding where the specific ships are,
Right.
you can just choose anything, because there's only one. It's like the Sudoku.
Right, it's like the Sudoku. What are you trying to minimize in the Sudoku? I don't give a damn. I'm sorry, I don't give a darn. So here's the cultural trivia question. Where does I don't give a darn play? Where does I don't give a darn play?
Somewhere in the outfield.
No. He's the shortstop. Considered by many the greatest comedy routine of all time, Abbott and Costello, who's on first? I don't give a darn as the shortstop. Right? For this, what are we trying to minimize? It doesn't matter. All we care about is finding something that's feasible. For the Sudoku, we're just trying to find something that's feasible. Any objective function is okay. And this is another point I want to emphasize about why I love linear programming so much. For many things, it doesn't matter what you put in as your objective function. You are just trying to find something that's feasible. Where might you actually want something like this? So almost surely the main application of this is not for individuals playing, one-person battleship. Where could this actually arise in the real world?
Maybe if you hit a ship, you destroy the whole thing. Like you don't have to destroy every single square there.
Oh, no. I'm trying to think where a problem like this might actually arise in the real world. Not just trying to play a game by yourself, but where could you actually use something like
Does
this?
this come up in cryptography?
Yeah, in like medical imaging or whatnot, where you might get certain information about what's going on in different slices. And trying to reconstruct what's the internal structure based on various things. And sometimes there might be a limit to how much radiation you want to shoot through somebody. Yeah. Sometimes you'll actually try to maximize the life expectancy or survival rate. But you could modify the game where, what if you were allowing yourselves to choose slices? Would you choose these as your slices? Would you choose maybe some diagonals? And maybe every time you choose something, you get more information, but at a cost. And if you put in too much radiation, the person dies. So there's a lot of applications for something like this. Could you extend this to more dimensions? Yeah. Would it be that challenging? No. And that's one thing that's really nice about this. You just add another subscript. Now the question is, how would you choose your variables? What would be a good variable choice? So we've got 2 minutes left. I think we can finish this.
Maybe something like an xij, and it's 1 if there's a ship there, and 0 if there's nothing.
Okay, so one possibility is just a pure simple, is there a part of a ship there? And in some sense, that's really all we care about. But we might know the structure of ships. We might know how many ships we have of length 1, 2, 3, 4, 5, etc. So one way is I just care about whether or not something is there. That's a great way to do this problem. Another way could be, this is 1 if we start a ship going horizontally at square ij. Or you could have different types of ships. You could have, if a ship of type T starts at I horizontally, at the pair ij and goes horizontally, and ytij would be a ship of type T starts vertically going down from the point ij. There's several different ways you can do this. For a lot of these problems, there's not a unique right way to write down your constraints. You can then do an analysis sometimes and see which way is better. How do you want to input the given information? Now, at the end of the day, you might be told how many ships of each type you have. That's very useful information. If I give you something like this. And so, if you just have xij, that might be a little bit harder to use the information that you know how many ships of each type there are. Because one of the problems over here is it's always a nightmare. If you go hit, hit, have you hit the same ship twice, or have you hit 2 different ships? Yes?
So even on this board, I think there are multiple configurations that will yield these numbers. Like I don't think this is the even acknowledging, okay.
That simple switch. There could be other ones.
Yeah,
possible.
I'm pretty sure they're like if you take the 2-3 ships, move them up 1, and move the 2 ship down 3.
Right.
Then it should be the board will look different and the numbers will still be the same.
Okay.
So sorry.
No. That's really good. So if we do that, as we move them up, it's not going to change the column sum. It will change the row sum and increase this one and decrease this one. So if we move that one down, yes. Yeah. So excellent. So unfortunately, that tells us that even knowing the number and type of ships is not enough to uniquely specify. So then the question becomes, how much information do we need to give? So I will segue from that to Sudoku. How many of you have done any Sudoku challenge? Solved a Sudoku, okay? What's true about every Sudoku you are given to solve? It has a unique solution, okay? Not every Sudoku has a unique solution. The less information I give you, the more possibilities. And in fact, there's interesting questions. What is the fewest number of squares you need to ensure that there will be a unique solution as long as you provide, is it 17? Right. So this might be considered invalid for one person's battleship precisely because there are 2 possibilities, at least. And we'll consider your 2 possibilities different than your 2 possibilities because in terms of just destroying things, yours is fine. But for yours, if we then actually fired the missiles, we would get a different answer. All right, excellent place to stop.